Welcome to today's class. I'm glad to have you there. We are going to look at the calorimetry and the method of mixture. The calorimeter is a device for measuring quantity of heat energy. We say when hot objects are mixed with cold objects, they attain the same temperature. And we say that the heat loss by the hot object is equal to heat gain by the cold object, provided that no heat is lost to the surrounding or no heat is absorbed from the surrounding. And we say it obeys the law of conservation of energy. Now here we have that heat lost by hot objects is equal to heat gained. Heat gained by cold objects. We can represent it with the letters heat loss by hot is equal to heat gained by cold. Remember, we have the quantity of heat Q is equal to NC delta theta. So in this case, quantity of heat loss is equal to quantity of heat gained. In other words, we can represent here with NC for heat loss, NC delta theta is equal to for heat gained by this cold object. We can have MC delta theta 2. Now we can now put their parameters. This one is losing heat by hot object. That means this is hot object. We can put H here, mass of hot object. Put H here, specific heat capacity of hot object. And now we now rewrite this and put temperature of the hot object minus, of course, when you mix them, they now have a common temperature, which is the final temperature. So we can designate it with this. Now here we have codes. We have code here. We can as well rewrite this one, giving us, in this case, because this one is gaining heat, we'll now take the final temperature minus the temperature of the cold water. So where NH is mass of hot objects measured in kilogram. CH is a specific heat capacity of hot objects. Theta H is temperature of hot objects. Temperature of hot objects. Theta F, temperature of, final temperature, please. Final temperature. MC, mass of cold objects. The same thing goes to C, specific heat capacity of cold objects. Theta C is the temperature of cold objects. Having described this, we'll now take some questions that we can use this formula to solve. Okay. Example 1. Calculate the final temperature of the mixture of 250 grams of water at 65 degrees Celsius added to 150 grams of cold water at 5 degrees Celsius. Neglect heat loss to the surroundings, and we are given that specific capacity of water is 4,200 joules per kg per Kelvin. Okay, we'll go. Solution. And the first thing that we do, bring out the parameters that are given. calculate the final temperature. That means we are looking for theta F. Theta F is unknown. A mixture of 250 grams of water a day. That means this is hot water. Hot water is 250 grams. And of course, because the specific heat capacity is given in kg, we'll convert this so that we'll bring the two to the same estimate. So we now have 250 all over 1000 will give us 0.25 kilogram. Temperature of this hot water, theta H, is 65 degrees Celsius. Mass of cold water, MC, is 5 degrees, 150 grams. Of course, we still need to bring the two to the same assignment, which will give us 150 all over 1000, will give us 0.15 kilogram. Temperature of cold water, theta C, will give us 5 degrees Celsius. Because it's the same substance, water, that is why we are going to use the same specific heat capacity. Now, specific capacity for both the hot and cold is 4,200 joules per kg per Kelvin. We apply our formula, and of course, our formula is the mass of hot water, specific capacity of hot water. Now, the temperature of hot water will come first, minus final temperature, which will give us mass of cold water, specific capacity of cold water, and then the final will now come first, because this one is getting heat, minus theta C. Okay, so we have mass of hot water 0.25 times specific heat capacity 4,200 equals the temperature of hot water is given to be 65. 65 minus theta F, and of course we are looking for theta F, is equal to mass of cold water. We use the converted one, which is 0.15 times specific heat capacity, the same water, 4,200 times theta F minus temperature of cold water is 5 degrees Celsius. Okay, multiply out 0.25 times 4,200. By calculation, everything will give us 1,050 into, we bring this one, 65 minus theta F is equal to 0.15 times 4,200 will give us 630 into, you bring this one, theta F minus 5. At this point, we can open this bracket. 1,050 times 65. By calculation, we have 68,250 minus 1,050 times theta F will give us 1,050 theta F equals 630 times theta F will give us 630 theta F minus 630 times 5. By calculation, it will give us 3150. At this point, we'll collect like terms. We now have this and these are like terms, this and these are like terms. So we'll bring this one over. 68250 plus 3150 equals, we'll leave this one here, 630 theta F. This one crossing over will change to plus 1050 theta F. Now we'll do the necessary addition to give us 71,400 is equal to, when we now add this to, it will give us 1680 theta F. Now let theta F the subject. Theta F will give us 71,400 all over 1,680. Now this cancel this. We'll now have 7,440 divided by 168. At the end of the day, our answer will give us 42.5. Therefore, we can now say that the final temperature of the mixture is 42.5 degrees Celsius. Okay, thank you. We'll move to the next one. Example 2. Hot water is added to 4 times its mass of water at 25 degrees Celsius and thoroughly stirred. If the final temperature of the mixture is 40 degrees Celsius, calculate the initial temperature of hot water. Solution. And of course, here we discover that the mass of water is not given. The specific heat capacity is not given. The question is for the table. So we continue. Now, hot water is added to 4 times its mass of water. Of course, this is cold water. Now, mass of hot water which is mH. Since it's not given, we can say let it be M. Mass of cold water, this is cold water. Now, mass of cold water, mass of cold water, which is MC. MC, we can have MC to be, since they say 4 times the hot water, so it is 4M. Temperature of hot water, of course, it is what we are looking for. We can call it the final, no, this is theta H. Then the mass of cold water, temperature of cold water is 25 degrees Celsius. If the final temperature of the mixture is 40, therefore the theta F will give us 40 degrees Celsius. Calculate the initial temperature of the hot water. Now, we say let the specific heat capacity of both the hot water and the cold water, let it be C. So we now move. Remember, our formula is MHCH theta H minus theta F is equal to mass of cold water, specific heat capacity of cold water, and final temperature minus temperature of cold water. Okay, mass of hot water is specific heat capacity of hot water is still C. So we say M times C times heat temperature of hot water. Of course, it is still theta H minus the final temperature 40 equals mass of cold water is 4M. 4M times specific heat capacity C into final temperature is 40 minus the initial temperature, which is temperature of cold water, is 25. Having stated like this, C can take care of C here, M can take care of M from here. We will now have theta h minus 40 equals 4 into 40 minus 25 is 15. So we'll open these brackets. We now have theta h minus 40 is equal to 4 times 15. 4 times 15 is 60. Collect like terms. Theta h is equal to 60. This one crossing over, the sign will change to plus. Therefore, theta h, which is the initial temperature of the hot water, will give us 60 plus 40, will give us 100 degrees Celsius. Okay. This is a final answer. Example 3. 100 grams of liquid L1 at 78 degrees Celsius was mixed with X gram of liquid L2 at 50 degrees Celsius. The final temperature was 66 degrees Celsius. Given that the specific heat capacity of L2 is half that of L1, find X. Now, there are two liquids here, L1 and L2. So we have mass of liquids L1 is 100 grams, which will give us, of course, by conversion, we'll have 100 over 1000. Therefore, mass of the liquid will give us, or we can say mH. mH is equal to, therefore, mH is equal to 0.1 kg. Temperature of hot water, which is the liquid L1, theta H is 78 degrees Celsius, was added to another liquid. So this, we can say MC is X. Now, temperature of this second liquid, which we don't know, is, we can say is the code, is 50 degrees Celsius. Now, the final temperature, which is theta F is 66 degrees Celsius. Here, given that the specific heat capacity of the first one, now specific heat capacity of the hot one is C. Now the cold one, which is the second one, specific heat capacity of the cold one is half of this other one. We now give you half C. Okay. We are now going to find X. As usual, we bring in our formula, which is NHCH into theta H minus theta final is equal to mass of cold water, specific heat capacity of cold water, and then final temperature minus temperature of cold water. Now we substitute. Mass of hot water by conversion gives us 0.1 times the specific heat capacity of the hot water, which is the C, into temperature of hot water, a hot object, which is 78 degrees, minus the final temperature, 66, equals mass of the second one, which is X, mass of cold water, we can have it as X, times specific heat capacity, the specific heat capacity is half of the hot one, which is half C, into final temperature 66 minus the temperature of cold water, which is the 50. Okay. At this point, we can now have 0.1 times C into 78 minus 66 will give us 12, equal to, we'll bring down our x times half C into 66 minus 50 will give us 16. Okay. Now we'll open this bracket. Well, before we open the bracket, 0.1 times C times 12 will give us 1.2 C equals, now half times C times 16 will give us 8C. 8C times X will give us, we'll have X, okay, we'll bring down X. If we bring down X, so now half times C times this will give us 8C. Now, C can take care of C from here. Now, we now have, make X a subject. X will give us 1.2 all over 8. Therefore, X, which is the liquid X, will give us 0.15 kg. Okay. Now this is the last of the questions. This is where we're going to stop the lesson for today. Please do not forget to subscribe so that once we upload further lessons, you will get notified. Thank you very much.